As a follow-up to talking about levers, something else that we need to discuss is the idea of a moment, to figure out what that word is, a moment, and something else called rotational or static equilibrium. Okay, what I'd like you to do is to grab a couple pencils, pens, anything like that, doesn't matter. We're going to use one of them as a fulcrum. You're going to rest it down. We're going to use a second one as a lever. And so if you set it on here, we can push on one end and get the other end to pick up, right? So a moment, what is a moment? A moment is a value that helps to quantify how bad the lever wants to turn. Okay, well, without thinking about that too much just yet, how can I make this lever want to turn more? Well, when I push on it, I could push harder, and it seems to want to turn more. Ignore all the rolling around, right? Another way to make it kind of easier is I could maybe adjust the distance here. And our problems are pretty simplified, we should note, because we ignore ever the weight of the lever arm itself. But changing the distance, that fulcrum, the weight of the object now is making it want to turn in that direction without me even having to provide much of a force. But if I provided a little force, if I just compare the difference between when the fulcrum is close to this tip versus moving it a little further away, I can tell that it doesn't seem to take as much force to get that lever to want to turn. So a moment, it has something to do not just with force, but also with distance. Okay, a moment is a force times a distance. Each force creates a moment. It creates an effect that makes the lever want to turn. So we are quantifying, kind of putting a number to how bad this lever wants to rotate or spin. Okay, so we are going to get two moments from a simple lever with one effort force and one resistance force. Again, we're going to ignore friction, and we are going to ignore the weight of the lever arm itself. Okay, this effort force, I just picked a first class lever. It doesn't really matter which type of class. This works for all three classes of levers. But for the effort force here, if I could push hard enough and overcome the resistance, the lever would start to rotate in this direction, which is a clockwise direction. And if the resistance could overcome the effort, it would push the lever, rotate it in the opposite direction. You can see if that force is going to win or overcome the other one, we're going to start moving in a counterclockwise direction. So these two moments, they're both wanting to create a turning effect on the lever. We know that there are times where we're in a deadlock, in essence. When I was trying to dig out a stump last weekend in my yard, and I had a shovel dug down in the ground, and I'm using the heel of the shovel as a fulcrum, and I'm trying to get underneath that root and pry up, there were times where I certainly felt like I was exerting a lot of effort force, but nothing was moving. Okay? And so that is an example of when we are in static equilibrium, or rotational equilibrium. And that is a point of reference basically when the two moments, not the two forces, the two moments are balanced out. Okay, and that can help us to try to solve for missing things if we consider that time and place, or that circumstance where these things are balanced. And so rotational equilibrium or static equilibrium, if they use those words, or they talk about in a word problem how much to overcome. So if we ever say overcome, think to overcome is just a tad past equal. You know, what's not to overcome would be when we're static, when we're not rotating. Okay, when we are, another word maybe to use here in layman's terms would be balanced. Okay, so if they use these words, how much to overcome, we're going to use balanced or these moments being equal as a point of reference. So if we know when that happens, we can go just a hair past that, just a little more force or just a little more distance here or there. Okay? So these problems are going to look something like this. You're going to start with the relationship of the effort moment being equal to the resistance moment. So this force, how bad the lever wants to turn, is not just how hard we push, okay? It's how hard and how far from the fulcrum. These two multiplied together, that product is what creates that. And so we have the effort side here and the resistance side there. So the effort moment, how bad this lever wants to turn, is the product of those two values. And so we're saying that when we're in equilibrium, this moment, this product, is equal to the product from the resistance, which is made of two things: the force of the resistance and where that force is located relative to the fulcrum, so the distance to that. So these two products are equal. The forces don't have to be equal, but the distances then won't. It's the product. So just mathematically, without worrying about labeling this, could you think of, let's say, take the number 12. Can you find different ways to create the product of 12, different pairs of factors? Well, let me think. I could create 12 by about 1 times 12. What if I had 1 pound of effort force times 12 feet? That would give me 12 foot-pounds of a moment. Well, another way that I could calculate, get a product of 12 would be, how about 3 times 4? So 3 pounds of resistance force times 4 feet would also equal 12 foot-pounds. And so here's an example where these values, the 112 and the 3 and the 4, could be replaced and plugged in here, okay, for a effort force and a distance to the effort, and a resistance force and a distance. You can see that the forces are different, 1 and 3. That's okay. I can still be balanced because the distances are compensating for that difference. Okay, so right here, notice I haven't plugged in any numbers yet. If you have any word problems that ask you to solve based on being balanced or being in equilibrium, rotational or static, either word, or how much force does it take to overcome the resistance, these key things, this is where you're going to start. You're going to start with the moments being equal. And often they don't give you moments in the problem directly. They're talking about forces and distances. Okay, so we don't have a number to plug in. And so the next step is to just rewrite this formula and write it with what a moment is. A moment is a force times a distance. So we replace the relationship of a moment equal to a moment as the moment calculation, a force times a distance. So we've got the moment from the effort, and the other moment from the resistance is created by the product of that force and that distance. Okay, and we get to here. Notice no numbers plugged in, and then it's from here that you would take the values they've given you and plug in the ones you know. And there are 4 values, so how many do you think will be given to you? Generally, they're going to give you all but 1. So which one they leave out, it doesn't matter. There's 4 here. They will pick 3 to provide somehow in the word problem and leave 1 as the unknown, so that you then just have to do a little bit of algebra to solve for the missing 1. And then you'll have the answer. Okay, so not every lever problem is going to be a rotational equilibrium type problem. We still might ask you about mechanical advantage over here. Calculate the mechanical advantage. Now, if we know the distances and things, know the actual forces, we can calculate that. But if we are missing a force or missing a distance, and we've got 3 out of the 4, we generally will use this relationship to kind of find when the lever would be in balance.